Hi, my name is Anika Valaru, and this is my lab report for Lab 4 in Physics 2211. So the purpose of this lab is to observe the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring using both a computational model and experimental data. The models and principles involved are Newton's second law, the spring force formula, force due to gravity formula, velocity update formula, position update formula, kinetic energy formula, gravitational potential energy formula, spring potential energy formula, and the total energy formula. Assumptions and initial conditions include no movement in the z direction, constant acceleration due to gravity of 9.8 meters per second squared, the origin is at the top of the spring, and there's no air resistance. So this is a preview of the path the object takes. The movement of the object from the computational model and its movement from the tracker data are actually end up being very similar. So the main idea is we are looking at arced and oscillating motion of a mass, so we're trying to see the path of this mass. The system is the mass and the surroundings are the earth and the spring, but for calculation purposes for energy, we say everything's in the system and there's no forces acting from the surroundings. So for the setup, the origin is at the top of the spring. For the axes, positive axis to the right, positive y goes up. For the basis, the stretch spring length is 0.7 meters, and this is when the spring and the mass are at rest at the beginning of the video. For tracking, the time interval is 1/210 seconds. The tracking point is the center of the mass, and the start point is immediately after the mass is let go. So this is what the video looks like. The beginning is cut off a little bit, but yeah. And so these are the still images, and on the right you can see X position versus time and Y position versus time. So for the coding process, I used the starter code and I put the tracker data into a CSV file and I use that in my code. The changes to the code will be discussed in the following slides. For the initial position, the coordinates were taken from the first point of the tracker data. So here you can see the mass of the ball is 0.402, or not ball, but the mass of the object. The initial condition, so you can see the initial position, which is taken from the tracker data. The initial velocity is 0 because it's immediately after it was let go. Gravity constant, spring constant, this is gotten from the video analysis. The relaxed length of the spring is 0.123 meters. And next you can see L, the length of the spring, so the ball position minus the spring position. L hat is L, but as a unit vector. S is basically delta L. And then next you can see the formulas for kinetic, the two potential, and the total energies. So inside the calculation loop, all of the energies are set as initial energies, and then you can see the force due to gravity, and since it's only the y coordinate, all the numbers are in the y position. And then the spring force is in the next line, and then the net force, and then you can have the velocity update formula and the position update formula, and then those are used to update the spring. The equations are the same as before, and then same thing with the energy equations. Delta is final or current minus initial for all the different energies. And then this is what the output looks like. For similarities, the starting position and the basic path taken overall are the same. For differences, the smoothness of the path travel are different. The tracker data path is slightly less smooth, but that might be just a programming issue. The paths are also slightly different. So this is the energies graph, and these are the X and Y position versus time graphs. So sources of error, the z-axis wasn't taken into account, so that might have caused some issues. Same thing with camera warps, and I might not have been completely consistent in the point that I was tracking. The spring constant might also be a little off. So is the energy principle satisfied? Yes, the energy principle is satisfied. Since all the forces are accounted for in the system, the work done by the surroundings is 0. So the change in total energy written as delta E in the graph below should also be 0. We can see in the graph below that even though the different types of energy change, the total energy remains constant. So the total energy, the delta E, ends up being 0 the entire time. You can see that in this yellow line. And so For the oscillation periods, I took the average of 5 periods from the graphs. So the X position period is about 1.65 seconds, and the Y position period is about 1.52 seconds. The oscillation based on the X position is slightly larger, but the two are very similar. The difference in the periods results in different spring constant depending on which direction is chosen. So in conclusion, the computational model and the tracker data are very similar, though their paths were slightly different. Thank you for watching my video.